Let me first just tell you a few things about what I'll speak about. And actually, I'm afraid that my talk will be a bit challenging because first I caught a cold, so I'm sorry if I'll speak not very clear. Second, it's my first time here at this kind of conference, and I'm having a bit different background, and most of my time in the last 10, 15 years I spent on compilers and designing hardware and making it more efficient. However, we start using a lot data mining, machine learning, Python, and so on. So naturally, I will tell you how we managed to solve some of our problems, basically with this technology, with Python, with scikit-learn. Another thing is, as I said, I expected to have 40 minutes of talk. From what I understand, I have 30 minutes, so I'll be quick. So it makes me, again, challenging. Also, we have a lunch afterwards, so if I see many hungry and angry eyes looking at me, I guess it will be time for me to wrap up. Okay, yeah. So and also one thing that the software which we're releasing soon, it's not yet released, but it's actually available. So all the things which I'll be speaking about, you can look at it. It's BSD license, permissive, and you can play with it, and you can give us feedback if you're interested in. And again, I hope you will find something interesting in my talk. Okay, so just a quick. By the way, I'm sorry that I like to move back and forward. If you see that suddenly you can't hear me, just like raise a hand. So I'll try to adapt. So just again, I wanted to spend maybe like 10 minutes of my talk on actually introducing you to the main problems which we have in computer engineering and designing compilers and designing hardware. And again, if it's not really directly interesting for you, I'm sorry. On the other hand, you are indirectly affected by this because I guess you always want to have the best, the most, the fastest software, the most probably energy efficient, so on. So even if it's not directly related to you, you may want to know what are the problems which are there. And okay, then I'll speak about this framework which we developed, which is basically a collaborative framework around several work groups which deal with compiler tuning, compiler design, software tuning, and so on. And then I'll speak a bit about the future work. Just a few things about my background, and why I'm spending some time on this is that it can tell you an idea why I'm doing what I'm doing. So originally I was not doing neither compilers nor data science. I was doing physics and electronics. And then later I did some machine learning, neural networks. Then I moved to computer engineering, for good or for bad, I don't know yet. It was a long time ago, and so I spent some time here in Edinburgh. Then I had an academic position in France. I was doing some stuff at Intel Scale Lab. I was heading a group there. And last year, probably, I had a middle-age crisis, so I quitted my permanent position, and I created the non-profit foundation, where I continued my stuff. And European Union thankfully supported me. And recently, I'm also kind of with my colleagues here in Cambridge who are trying to see if we can do a startup. So, and this is related, again, a usual disclaimer that present work opinions are my own because I have been spending lots of time actually collaborating with those companies, so I can't say that it's my opinions, it's not their opinions. Okay, now since it's the last talk before the lunch, and I don't know if you are sleeping or not, so I just want to wake you up, and I know that it's not your domain, but out of fun, does anyone know what this device can do, and what is it actually, what is part of the big device? So it's just like some electronics, and you have an input X, Y, you have a current going through, and you have this function. So this, what can it be? Anyone knows? Even if you're not doing electronics, you may know what this is.
It's a latch.
Sorry? It's a neural network. It's a neural element. It's basically 20 years ago, as I said, I didn't do all this compilers and so on. I wanted to, it was my first research project which I joined, and it was on trying to build brain-inspired accelerators and basically converting the software neural networks into hardware. And I mean, I had to say that we failed. I mean, if we didn't fail, probably by now it would not be IBM who would be doing all this neural stuff, but we would be doing it at that time. But we failed. And we failed at that time mainly because all our modeling was too slow. The hardware which we use, it was breaking all the time, so just modeling this element, it was taking me 2-3 days on that hardware which we had, and by the time I was getting, like, I was young at the time, I didn't have like white hair, I was running to this computer thinking, oh, I will get all the results, and it just crashed after 2 days, so it was awful. We paid our bills for the power consumption. Now everyone speaks about that, oh, we have a problem with energy. I mean, 20 years ago we had to pay ourselves to get this grid of our own computers which were communicating through this COM port, and it was awful, and too much data, so we failed. And this probably basically moved me to, again, as I said, for good or for bad, I switched to computer engineering because I thought I wouldn't be able to work on my topic if I wouldn't solve this problem. And again, I was young, so I thought I would solve this problem like in a few years. Now, 15 years later, so we didn't yet solve it. So, but again, I think we found some good results. So just again, very quickly, like what I call back to basics. So as myself, as a researcher, what I wanted at that time is that I didn't care about which hardware did we have, which software did we use. I wanted to get my idea, neural network, and I wanted to get result as fast as possible. At the same time, I wanted to minimize all the costs. So costs is like energy, power consumption, have memory, data footprint. You can have some, you may want to guarantee some constraints, and it's like, again, I said, power budget, but if you now, on a mobile system, you want to have real-time constraints, for example, you don't wait for like an image to video to be updating for ages and so on. So these are the things which we care about. And you as a user, you expect that the hardware and software which is given to you, that it's working perfectly, right? So, or at least you expect that what you pay for is good. Is it really true? So when I started looking from my idea, when I get to this like real results, so now you start designing your algorithm, you get to, from high-level algorithm, you get to your code. Application can be in high-level language, can be low-level, then compilers are kicking in. You, in Python, you may not know what is happening. There was a good talk yesterday on that there is a JIT now and so on. You may not know about this. How it runs on the system, on a virtual system and so on, now you have no even idea where it works on. And of course, we have like, Intel is producing 10 chips per year, so, and they're giving you new chips until like, try them all. You don't know which are the good, which are the bad. You look at the cloud, Amazon, Google, what are the most cost effective? You don't know. Okay, so 20 years ago it was simple. You had like one processor coming each 2 years. You had one compiler and you had your like one library which is not changing. So what do we have now is that we have a mess. So we actually don't know how to choose our system. So again, I'm happy if you think that your system is working well. It's good for you. Maybe I'll kind of tell you it's not good, so you will start questioning your service providers, and don't like blame me for that. So. And the problem is a fundamental that the complexity is rising, it's not getting simpler. So if you look at all the possibilities, all the design choices which you have, all the optimization choices that we have, they're huge. And we need to look at multiple objectives, tuning objectives. And even looking at your system, you have multiple users running on the same system, you have like contentions. You don't know how to make the best out of it. And at the same time, speaking to my background and compilers and hardware, we don't have even a common methodology for benchmarking, for comparing systems and so on. So it's all mess. I hope that in your domain it's better. I hope. In our domain it's not. It's actually really awful. Okay, so just now a few examples again to tell you how difficult is my problem at least, and why we started using machine learning is. So this is an example that let's say GC compiler and similar trends are in LLVM. Why I speak about those compilers that even if you use Python underneath, you would still use those low-level compilers. So on there, if you look at 15 years ago, so we had like, I'm showing you, I'm not sure if I'll be able to show you like this. Doesn't work, sorry. Okay, I'll speak. So here what I just want to show is that if you look at the possibilities inside the compiler, you have many different optimizations which you can use. And the blue line is showing you parametric optimization flags. So each, basically for your code, when you compile, you can choose this parametric flag and you can choose some parameter. And 15 years ago, there was like 5 of them in GCC. And if you look at Boolean flag, yes or no, let's turn on optimization. There was like about 50. So now by last year, so we have around 140 parametric optimizations. So what it means is that if you want just to compile your code, you need to select 140 dimensions to understand what will be the best optimization, and the same 220 Boolean flags. Now, I'm not speaking further about if you start looking at OpenCL code, OpenMP, MPI parameters You have frequencies which you can play with and so on. So it's all a mess. Okay. A few more things. Again, this I think may be fun for you. So just one of our customers, when we look, they asked us to look at their code and its image processing application. And we just start looking, randomly selecting those flags or parameters. Just random, stupid, nothing, no machine learning, nothing, just plain stupid stuff. And what we get for free, we get like 20% improvement on execution time. So here you have, like, say, size of your produced code versus execution time. And for companies like Google who do Chrome and so on, they want to both have the best speed up for your application and then pack it as much as possible. So then if you look at the Pareto, you see that GCC, if you take it and you compile it and you expect that it's good, that for free you can get like 20% execution time improvement. Is it a lot? So for you, you can say, but who cares? I mean, for us, 20%, we need like 20 times. Now, if you say, that's what I also thought. And then someone used this technology from weather prediction systems in US. And the same, they told me, you know, we got with this system 5% improvement. So I start laughing. Okay, 5%, who cares? So you don't understand that 5% improvement in our code, weather prediction, we run 24/7 for 365 days. So it gives you like $100,000 bill reduction per year, because it's just we use less energy and so on. So this is all important. And again, I'm saying that also what is important, if you start playing with optimization, it's not just that you can get speed up. You can kill your performance by getting a wrong flag or something, because you can get like 5 times degradation in performance if you just like switch a wrong flag. So these are just ideas. This I will not start moving much further. I just want to say that, again, in compilers, we use like a few benchmarks to tune the code, and which are like here on this side. And this PerX, it's a benchmark, and this which speed up you can get with kind of automatic tuning. And these compilers are using this. If you start looking at the realistic codes, what we do, that you start getting really like very high speed ups and so on. So what I want to say is that our systems are really inefficient. What you get, you can often get like 2, 3, 4x speed ups for free. And instead of buying the new system next year, whatever, which would claim you that it would get twice the speed up. So these are well-known things, and I'm not saying something new. The same, what we started doing at the end, I don't know whether my system is efficient or not. I started looking at historical data. For example, I used these neural networks 15 years ago, and which was motivation to move here. And I started looking how my code behaved over the last 15 years on all those different systems. So I used like C, C++, I converted to Fortran, I use Java, use recently Python. We use CUDA, OpenCL. And then if you look at all this technology, and then you look at all the compilers which I use, starting from this old one, 4.1, to on different machines, Android. So you get some very strange graph. I don't want to get much into details, but the idea is that obviously, most of the time we're completely inefficient. So if you look at you can plot those Paretos for execution time, for energy, whatever you want. And then if you have this historical data, you start actually realizing that, my God, all this time. So 5 years ago, 10 years ago, on the same system, maybe I could get results 5 times faster instead of waiting for 2 years to get like another machine. So this actually is scary. Okay, I just want to persuade you that our stuff is interesting and that it's useful. Okay, now, what do we do? So looking at this, and this maybe you start kind of seeing how I connect our research with what you are doing, is we start looking, okay, we have this kind of problem which is really can be used by machine learning. So we have all those compile optimizations, we have algorithm parameters, we have hardware properties. So why not to start using machine learning and basically start predicting, start training your models based on this previous data which you have, which I showed you, and then start predicting optimization, start predicting maybe the best parameters and so on. Okay, sounds like an easy idea, okay? Is it really easy? So again, as I said, how it would work, how I would envision it, how I was envisioning it like 15 years ago. For me, it was like, oh wow, it would be so simple, I would solve it like in 1 year. Yeah, well. So this traditional thing, what you see here with how you build the knowledge, so I don't want to get into details here. It's obvious for you how machine learning would work, how you would collect data, how you would train it, how you would build active models. This was an idea. What happened with this idea? What happened is the following. Yes, we managed to produce 4 or 5 years ago a plugin to GCC, which was inside main line where we could actually, whenever you compile a program as a user, we would start extracting some features from the code. We would start sending your data when you run the code to our server, which was ctuning.org. And then basically there we're building models, and then when you have a new program compiling, we would first send a request with your features of a program to the server, and it would give you back what would be your best optimization. So, and this worked in-house. However, when we opened it and IBM made the press release in 2009, 2 days later, my colleagues at Tenri at the time I worked, they started complaining, said that our servers died and network died, and we checked what, in just 2 days, people, not so many users, I think we had around 100, they downloaded it and started sending data, huge amount of data. And I didn't think about this at that time, you know. So now, again, we have this big data buzzwords and so on, but we started facing it as well. So we had to solve it. So this idea of this nice idea of machine learning, again, turned out as a very complex problem, as you know very well. And again, I think additional problems which we have in comparison with what I see with some other sciences is that we can't just have a training set which is there for 10, 15 years and not changing. You have like images sometimes which are there forever. Our system is changing all the time, each day. So the model which I'm building next day, library changed, compiler changed, it's changing all the time. The target is moving. So it really makes it difficult even how you characterize this, how you extract features, what do you do with that? Results are unreproducible. Again, when you speak about a machine learning model, okay, you have input, you have output, and if you don't use some probabilistic approaches or whatever it is, you have a deterministic output. Here you run your code on a system, and you get performance number, but your performance number varies by 3 times, and you don't know if it's due to your optimization or it's due to someone else running something in the background, it's virtual machines changing. You don't know. We need to attribute this. All our compilers, hardware, it's not used to be exposed to auto-tuning or to machine learning. So I was working with IBM with a very good group on machine learning, and we spent probably 4 months. They were trying, very good machine learning group. We were trying to tell them what you are doing. We have some compiler flags, we have some passes inside, so that they don't understand. We're not on the same page. Okay, so it's another problem. And the same MySQL databases. Again, I was speaking about this 5 years ago. The data is changing all the time, so we couldn't use it because if you start changing all the tables, descriptions, so it's changing all the time. Okay, so now I'm done with my problems and how now we can solve it with possibly Python and other techniques. So this is just one more comment. It's funny. So 4 or 5 years ago, I was very depressed because I didn't know where to go from this because it's like really complex. And a few years ago, I was giving a talk in US, and it was funny. It's practically everyone, they were doing some completely different things, data science, but everyone was coming to the stage and saying, our life was miserable, but then we found Python, we found JSON, the format, and it changed our life. And then I was the same. I was going out on the stage and said, actually, it was the same for me. So it was magic. I found Python, I found JSON format, and I realized it's actually very easy to convert our problems into kind of much more usable way and extensible way. So we have this kind of no schema free format, which is very extensible, and it's much more easy to add things there. So what I started doing, I also realized that for us, it's not about machine learning, actually, in our problem. It's about data management. So I have lots of data to deal with. We have many data sets. We have like thousands of data sets that change. We have compilers that are changing all the time. I want to sort out this mess, and I want to sort out it on my computer. I can't use third-party tools because we just, even on my computer, it's changing all the time. So I started realizing that, first of all, I need to group all this mess, files, and so on into some kind of subgroups, which what I found, like, for example, we have programs. Now I'm speaking about maybe some obvious things, but again, this idea behind what we do with the framework, so if it's obvious for you, I'm sorry. But who knows, maybe you will find something useful, or maybe you will tell me that it's solved already, and then it's good as well. So what we did, so we grouped those, we see different files which we have programs. We know that they have some common meta information, which how you would compile it, which data sets they take into input, and so on. Then we start looking at the data sets. It's another group. We have the files. We have their meta, which can be features, weight, height. If it's an image, it can be something else. We have some common functions, which we need to do with them as a research. Okay. We have some packages which we need to deal with, like for installation when we deal with different GCC and so on. Again, they have similar meta and so on. So we started thinking is that why not to kind of provide some wrappers, Python wrappers, which would actually provide you an access to this data which is on your system. And you would also like provide some meta information in JSON. And you structure your files, so all these things which I have locally, which is usually a mess. You do your experiments in 2-3 years, you try to run them, you need to find all your data sets and they're scattered all over, you have no idea where they are. So here we want to make such kind of structure and we want to provide functions around those wrappers which will allow you to unify and access to this data, okay? And basically what happens now is that we suddenly realize that, oh, but we now have this kind of structure which is still local, we're not locked in on any system, which is like on my machine, I start now putting all my data into something called like directory called CMR, then on my module it's next level directory, then I say name of my the package dataset and so on, and I provide some meta information. And I could show you more how it works. Again, it maybe sounds obvious, but the idea is that it provides you a structure which now you can always, for whatever you do, like new data sets, new compilers, and so on, you always know how to find information. And it's all on your local machine, so it's not locked in. You don't locked in on any databases, on other web services. It's all local. Okay. At the same time, I can just find all my data with kind of unique ID, because for both module and the name, sorry, I'm just used to, and to the name of the data, I provide some UIDs and so on. Obvious thing. But again, now, when I do research and when I say, I want to find the data set, what do? I'm actually querying my system, and it would give you some seed and would give you information where it's where you can find it. And then what happens is that we wrote a very small what we call CK infrastructure, which is 200K. It's available online, which basically glues in all those things together on your system. And it's again on my system. I'm not using any web. I don't have any dependencies, just pure Python. And basically what I can do is that I can do some common functions like CK list program. It will tell you all what is on your local machine. It's not databases. If you want to change them, you go again as a file system. You go change them, do whatever you want with them. You can call them from IPython, Python, and so on. And you can have the same web service, which just input-output is JSON, is a dictionary. Extensible. I could speak much more about this here, but I don't want to. Again, if you want to know more, we have a few papers, and also talk to me. I can tell you more about this. I just want to get further how we use it. So what happens now, why do we need is that, don't forget that now what I see when we want to create our experiments and share them, now we use IPython notebook. It's good, it's really nice, but you need to somehow find your data on your system, and either you hardwire it or you do queries to databases. Here we just have we converted all our ad hoc scripts, whatever it is, into these CK modules. So now you can actually, instead of hardwiring directly the path and so on, you just query the system and so on your local machine, so you just slightly changed files. I'm using it for 3 years. I'm not trying to make people happy. I actually make my life easier. But then what now we do for machine learning, and it's getting more interesting. So JSON is very extensible, so you don't have a schema. So what we do is that when you compile a program, you provide the wrapper before compiler, but then you gradually expose features, characteristics, and behavior of the system, and you can provide like execution time. You start putting all this logic inside, so basically you start monitoring your information flow within your system. And what it means is that you kind of abstract your system from the changes, so even if the system changes, you still go through wrappers, so your system doesn't break. And you start using just pure mathematical functions. So any component, you compile program, you run it, you go through the wrapper. You now just start monitoring the behavior of the system and model it with machine learning, where it becomes just a function, what you saw like before. Of your choices, optimization choices, which you can again expose very easily through JSON. And it's, again, you don't have to expose everything, you just gradually expose with the community. Function of your choices, features, and the state of the system. And then module becomes like self-aware kind of idea, so you can start learning and tuning it. Okay, and then what is more fun is that with such kind of approach, you can build those kind of workflows, you can replay experiments and so on. And still, again, it's on your machine. You don't need to be locked in or any other system. It's portable, or we run it on many systems. Okay, another fun thing is that, okay, JSON is not very well prepared for, we need vectors usually for machine learning. So JSON is not well prepared for this, so we just decided to use what we call flat format. So we flatten all these dictionaries into vectors, and then we can start actually using, we can tell what are those vectors, you have ranges and so on. So the system becomes auto-tunable automatically and self-learning, okay? The last thing of the framework, just to tell you what we do, is that now with such kind of repositories, what we have, local one, we just suddenly realize that when I collaborate with my work groups, we just put them on Git, someone pulls it, and the system starts working. So all the experimental setup with all the data is there, and you are not again locked in on any database. You don't need to install it. You install it in 1 minute. Okay, it works. So with those wrappers. So this was a really neat thing. On top of it, we can provide Elasticsearch. We use it which actually transparently index those meta information, so that if you want to really fast queries, you can do it, but you don't need it. This is a system which is very simple, and it helped us. Okay. Finally, now about just how we used it, and I think I have 10 minutes, 5-10 minutes, I think. So I just want to tell you a concept about how we converted all this mess which we had. I'm not saying that we solved everything, okay? That would be too nice and too naive at the moment. But I think we found this idea of how we convert all this mess into this machine learning problem. And now we can actually use Python, JSON, plus standard machine learning packages for this kind of learning, machine learning, what we do. So it's really nice. And what we do again, in computer engineering, people don't know where to start looking at. So some people tune compiler flag and so on. We start doing like physics. I used to do physics. So we start looking at the whole system, how it behaves, execution time, very coarse grain, and then we start digging in. When someone as a community can provide more optimizations, more features, and so on. And JSON, Python are perfect for this. Okay, again, don't want to go much deeper into this. Example of machine learning. Otherwise, so finally, if people probably kill me if I would come here and didn't speak about machine learning. So how we use machine learning? One of the cases is what we had was a real example. You have an application. I can't speak which, or maybe I can speak about which applications. That yeah, it's a real-time video processing application, which actually in itself had some machine learning, but it's not how we use it. But okay, and it's ran on mobile systems. So we had two systems from Samsung, Chromebook 1, Chromebook 2, with different parameters there. It had a GPU, 4-core, and has 2-core ARM processor. And the point is that now when you have, or at least 4 or 5 years ago, when you have GPUs, everyone say, oh, forget about CPUs, just use it on GPUs. Okay, if you have HPC system, that's good. If you have mobile system, GPUs and CPU actually GPUs are not necessarily much more performance efficient, much faster, I'm sorry. It depends on the cores which you have and so on, because they're limited with the size and the power budget. So in fact, on mobiles, it's not necessarily better if you run a system on GPU, because then you also have memory transfer cost, which you need to take into account. So here what we did is that we started looking at this application. This application was actually really, people had problems on those mobiles. It was always dropping performance. So they expected that FPC would be like 10 frames per second. It was always like 3, 4, and it was always jumping. So what did we do? We just trained, we used our system, which basically provided wrappers, start collecting all the features which you look at, say, what is the frequency, current frequency of your system, of CPU, of GPU, what are the parameters of it was OpenCL, of your global work size, what are your image sizes, and so on. Then we put it through the system, so we see this information. And then we started building the models, and what we see, again, this was done with Ceylon, it's an obvious usage. That's why I'm not getting deep into how we do it. But the point, what we do is that basically it would find that on y-axis, you divide execution time of CPU on GPU, which means that if it's more than 1, it's better to run this kernel on GPU and otherwise on CPU. And these are all the points which we had in the training set, and it's again, we just collect them and so on. So the model was very simple on the first Chromebook. So you would see that just depending on the work size and so on, or which basically relates to your image size, you would run either on CPU or on GPU, and most of the time you would run on GPU. That's what people expect. Then the same model which it runs, because we use we can continuously learn, and when we build a model, when new data is coming, we actually continue validating it, like active learning, as you know. So what we do is then we move to Chromebook 2. Again, this is the idea when you move from one machine to another, is your kernel performance portable or not? So what we see see that with model, actually, model is behaving very badly now. So with empirical knowledge and with the validation, we see that it's dropping to 74%. And if you look at originally, the point was that CPUs became much more powerful on the Chromebook 2, while GPUs didn't change. So what we do, again, we just continue calling the model and we improve it. And now, after a while, we can get some really crazy models, which still gets you to 96%. And you can do now adaptive scheduling. So you always, basically, for your kernel on whatever machine it is, with active learning, you will get the best performance, what you have. So this is a simple example, but this gives you an idea of how it works. And again, the point is that with all this data, it's online. So all this data goes through our web server, so you can see the data and you can improve it. You can provide your own data and so on. So workgroups found it really useful to use. I have 2 more slides, and then I'm wrapping up. This is just the last thing. It's okay? Okay, super. Okay. Another interesting thing which thing which made me very satisfied with the idea what we do is, so I spent, 10 years in computer engineering, and when I read papers which are there, I'm scared, particularly with my physics background, because people run the code once, not even 2 or 3 times. They don't give you variation of your execution time, models, and no one ever knows how they're built. No one ever speaks about like if there were some features and so on. So people yeah, we have some results, trust us. So with our approach, actually, reproducibility comes as a side effect, because there, if something doesn't work, first of all, you expose it, you see it. And just one funny example was, I used this framework to make a demo about a year ago, and one night before, and this is obviously understand that one night before you shouldn't change your demos. So I want to change my demo, and I want to show that we run the same system, one kernel, on this laptop with exactly the same parameters. So I don't change anything. I just want to run the same code, run, stop, and get the execution time overnight. And the idea, I wanted to show that the execution time will be, probably the variation will be small if you don't change anything in your system and so on. So in the morning I wake up and I see this, the execution time was like, say, 10.5 seconds and the variation was 6.5 seconds. So now, in our domain, first of all, if you get this result, you just scrap it. You don't tell anyone about this, just remove it, okay? First of all. However, if you start looking at it and you start looking at the variation, what happens, so we have the statistics in my system, you get this. This is a distribution of execution time, and my expected value was there on the left, about 6 seconds. However, overnight, most of the time was spent in 24 seconds, the execution time was. Can anyone tell me what happened? And this is like my more or less last thing before you again wake up before the lunch. It's the same code, runs the same time on the same laptop overnight, and suddenly instead of 6 seconds, it's get to 24 seconds. Okay, so, okay, fine. Actually, this part, when I speak to compiler guys, or hardware guys, they usually tell me what happens. Okay, so this laptop, I was using it in those sockets, and overnight I switched by accident, you know, this UK socket. So the power was off. So for a while, the laptop was running fast on 6 seconds, but then adaptively it went into saving mode. So it gets your frequency 4 times slower. So it runs on the lower frequency, and that gives you a result. If you scrap it, you don't even know about this. Here, what we do in our system, we say, oh, but we forgot frequency is a feature. We need to put it into system. So we'll put it into system, and next time your experiments, which you continue running, they spread you different frequencies into different experiments. So this is the idea of how you can actually add more features, and you build this knowledge, what we call, and you extend it. You don't scrap results. And it's useful for conferences and so on. And my dream is, I get from this thing, which was 10, 15 years ago, of which this mess in computer engineering, I want to make our computer engineering a science. And you know, this is the point that when you speak about compilers, computer engineering, it's not sexy, unfortunately, but it's needed. And now we can actually combine both cool things, geeky things from compilers and so on with data science. And it's actually getting really excited. So last 3 years, I saw a big drop in students coming to compilers, to hardware design and so on. It's a well-known problem. And suddenly I see again, particularly people were talking to me about this. They say, oh, wow, this is such a cool thing. Then we can do some funny graphs, machine learning, we can improve models. So it's a completely different attitude towards this problem of performance portability. I'm happy with that. I hope it will continue. Conclusions. So the new framework, the framework which I presented, it's existed for about 2 years now, and now I'm building from scratch a very new version, which is tiny. It's available there, but we didn't yet officially announce it. So you are the first ones who actually see the link. Don't tell anyone. No, actually tell everyone if you want to, or look at it if you're interested. We have a live repository, again, not publicized, where we show we can make reports with interactive graphs which just go through the system. And it's, again, it's like few lines of code, and it's all doing this with your data. We'll prepare the documentation. ACM found this project interesting, so we'll have a work group meeting in a few weeks in ACM headquarters in New York, where they speak now about reproducibility a lot. So they found this approach very interesting, so I hope we'll continue it. And of course, we're raising funds, so wink, wink, if someone is interested to collaborate with us or do something more. I mean, we have now first round of funding, but if someone is interested to collaborate, we're very happy to discuss it. So I'm done. Thank you very much for your attention. I hope it was interesting, related, and if it was not interesting, at least you will enjoy lunch, I hope. And we have those like Twitters, all this usual stuff, and a few publications. Okay, thank you very much.